Hello students, welcome to the physics session. Today we are going to start with the new unit named Properties and Uses of Magnet. This unit falls under the theme of magnetism. So, before starting the main concepts of magnets and their properties, we are going to do various investigations to learn whether and how magnets behave. Okay students? So, let's start with our very first topic, that is investigation 6.1, that says identify magnetic and non-magnetic substance. So, in this activity we will learn how we can identify various components into magnetic and non-magnetic substances. Now, you already know what are magnetic substances, students? Magnetic substances are those substances that attract towards a magnet. Right students? There was one more property for magnetic substance that they show is that they can be magnetized. That means they can be converted into artificial magnets. Right? On the other hand, what are non-magnetic substances? The non-magnetic substances does not get attracted to any magnets. So, we already know what are magnetic and non-magnetic materials. Now, in this activity, we will learn to classify them into the two groups, that is the magnetic and the non-magnetic. Now, for this activity, what you need to do, you need to collect common objects that you find near you. For example, you can take a glass tumbler, paper clips, common pins, stainless steel, plate, silver spoon, razor, plastic ruler, a rubber, crayons, pins, scissor, and then what you need to do? You need one more component, and that would be a magnet. Your activity is to try to attract each of these components using the magnet. The components which get attracted to the magnet will be classified under the category of magnetic. On the other hand, those components which cannot be classified or which cannot be get attracted to the magnet will be classified as non-magnetic. Now, for this activity, you can do this with as number of objects you can find at your place. Eventually, you will find out all the objects which are magnetic and all the objects which are non-magnetic. Okay, students? Now, we are doing some of the activities to understand various properties of the magnet. We need to investigate the strength of the magnet in activity or investigation 6.2. So, let's begin with this activity. In this activity, students, you need to collect some iron pins or all pins that are commonly available on any stationery shop near you. What you need to do, you need to spread some of the common pins that you see here on a plastic plate. Now, be sure that you use a plate that is not made of magnetic material. That means that could not be attracted to the magnet. Now, when you place some of the common pins on a plate and bring a bar magnet near it, that means we first spread some of the iron nails over it, the pins over the plate, and then we bring the bar magnet near the plate. What you will observe after this, students, when you bring the bar magnet and you again lift it up, there will be some pins that get stuck to the magnet. That is what magnetic materials are. They get attracted to the magnets. But there is a very particular thing that we can notice here. And what is that? We can notice that there are pins on the edges of the bar magnet, right? The most of the pins are clinging to the edges, and there are no pins that are in the center of the magnet. That means what, students? This means the strength of the magnet is maximum, where it is maximum at its ends. Right, student? So, even if I take a not a bar magnet, but a U-shaped magnet, right? And I bring this U-shaped magnet near my pins. What we will observe? We will observe that in the U-shaped magnet, the pins get clinged on the edges. So, irrespective of the shape and the size of the magnet, the strength of the magnet is maximum on the edges. That means at its end. Okay, students? We are going to learn a new property of magnets, that is called the directional property of magnet. Now, students, you have already learned this, that magnets have two important properties. Number one, they have attractive property. That means they attract the pieces of iron. And the number two is the directional property. That means any magnet, when suspended freely, will always point towards the north-south direction. Now, how we are going to prove this? To prove this, we are going to do the investigation given here. Now, for this, we will require some of the materials. So, as you can see in the image and as you can see on the right side of it, we had already written the materials required. What are those? The first material will be a glass jar. So, you will require a glass jar and you need to fill it with water. So, these are the two basic things that we are going to use for our investigation. The other thing is a magnetic compass. A magnetic compass is, students, used for finding out direction. So, if you had ever done camping, you might have seen a magnetic compass that is used to tell you in which direction you are actually moving. The next thing is a bar magnet. This is our test magnet. This is used to test whether the magnets actually show the north-south direction or it is just a theory. So, we are investigating the directive property, whether it is true or not. The last thing is a piece of wood. Now, we know wood has a property that it floats on water, right? So, that's why we are using a piece of wood in this case. Now, for the setup of the experiment, what we are going to do, number one, we are going to use the magnetic compass and we are going to mark the direction north, east, west, south using the magnetic compass on a chart paper. Let's say it is my chart paper and I had marked the direction by the dotted line, that is south, west, north and east as shown here. Right, students? Now, what we are going to do, we are going to place the glass jar over that chart paper sheet as shown in the image, so that I can see my direction and the glass jar sits in the center of the whole setup. Okay. Now, in this glass jar, we already have water. What we are going to do next, we are going to put the rectangular wooden piece inside water. It will float. On that rectangular wooden piece, we are going to place our test bar magnet. The bar magnet we are using to test the directional property. Now, when you will put the bar magnet on the wood, it might be moving, right? So, you need to give it some time to rest. The time it takes to rest, you will notice that the magnet gets aligned to the north-south direction as shown in this figure. As you can see here, the magnets after floating or coming to rest, it will come in the north-south direction. Now, if you want to test it again, just give it a flip. Let's say you rotate it, the magnet, by 90 degree. So, your magnet becomes like this, right? Somewhere like this. Now, you again give the floating wood some time to rest. After it comes to rest, you will notice that doesn't matter you shifted by how much angle, your magnet will again align itself in the north-south direction. This shows that the magnet always points in the north-south direction. This is called the directional property of magnet, and we can define it in one line as a freely floating or suspended magnet always points in the north-south direction. Okay, students. Now, Why this happens? Because the magnets have a very common thing. You might have observed whenever we draw a magnet, we always write down N and S on both the sides or edges of the magnet. Now these N and X are actually defined as the poles of the magnet. These are the places where the strength of the magnet is maximum. So these edges are nothing but the poles of a magnet. So let's learn about these poles. The maximum number of pins cling to the bar magnet. We already did this in a previous activity, that if we try to stick some iron nails or iron pins to the bar magnet, the maximum number of pins will stick to the edges. That means towards the end of the bar magnet. These ends of a bar magnet where most of the magnetic strength is located. Now student, this is important. We had done this in previous activity, that the magnet's strength is maximum at its edges. Now these edges are called magnetic poles, as we have defined already. Now what are these magnetic poles called? One is called the North Pole, the end of a freely suspended magnet which point towards the geographical north. Now we know, due to directional properties, the magnet always come to rest in the north-south direction. Now how does it come to rest in the north-south direction? Because it is actually pointing towards the geographical north point of the earth. So the end of the freely suspended magnet which points towards the geographical north is called the North Pole of the magnet. On the other hand, the South Pole is the end of a freely suspended magnet that points towards the geographical south. So the point which points towards the geographical north is called my North Pole, and the point that is pointing towards the geographical south is called my South Pole. Poles are very important for a magnet, and we are going to learn more about these poles in various activities that we are going to do in next videos. Okay students? Now what we need for this activity are two simple components. Number one, a magnetic needle, and number two is a bar magnet. Now what we need to do our experiment to is that we will suspend the magnetic needle using a thread. We know that all magnets have the north and the south pole. Now using your bar magnet, first thing you need to do is bring the north pole of the bar magnet near the north pole of the needle. What do you observe when you do so, students? When you bring the north pole of the bar magnet near the north pole of the needle, you may observe that the needle gets separated or deflected. It gets away from the bar magnet. That means the bar magnet is applying a force of repulsion towards the needle. Let's try it for the south pole also. Now for the same needle suspended with the thread, if you use the bar magnet and this time you bring the south pole towards the needle, what do you observe? That if you bring the south pole of the bar magnet towards the south pole of the needle again gets deflected and try to move away from the south pole of the magnet. This means the north pole of the needle is repelled by the north pole of the bar magnet, and the same is true for the south pole also. The south pole of the needle is repelled by the south pole of the bar magnet. Right students? So when this happens, we can conclude that similar poles, that means the north and the north and the south, those are similar poles. Similar poles of a bar magnet repel each other. So my conclusion from this activity is similar poles of magnets repel. Right, students? What about if I change my activity with a very slight alteration? In this case, I want to test what will happen if I bring the different poles together. Let's say in the same setup, I bring the bar magnet south pole towards the north pole of the suspended needle. In this case, students, you will observe that the north pole of the needle and the south pole of the bar magnets get attracted to each other. They will move towards each other. The same will happen if you bring the north pole of the bar magnet towards the south pole of the needle. In this case, again you will see that the needle is attracted towards the bar magnet. So by this activity, we see that the south pole is attracted towards the north pole and the north pole is attracted towards the south pole. So in this case, we can conclude that opposite poles of a magnet are attracted. Right, students? So these are the two properties that we understood by doing this activity, that the poles of two different magnets are attracted if they are opposite poles and they are repelled if they are of the same polarity. That means they are of same type. Now, we understood that poles of a magnet exist in each of the magnet, right? I'm just penning down what we just learned. One is opposite poles attract, right? And what about similar poles? They are repelled, right? Now, there is one more important thing about these poles, students. When we talk about poles of a magnet, the strength is not just at the edges. It is a bit inwards to the center. It's not just at the edge, but a bit of a distance from the edges. Fine. Another point that is very important, in case we use a bar magnet and we use one pole, let's say the north end, and we try to attract another magnet, another bar magnet, you may see that it may repel and it may attract. It can do both with two other edges. But if I take an iron piece, we know that iron piece is attracted no matter which side you are using of the magnet. So, can I differentiate between a magnet and an iron piece because both are getting attracted? I can. How? By the use of the property of repulsion. I know that magnets will always attract a magnetic substance like iron. But in case of a magnet can attract and can repel depending on we are approaching the magnet through which pole. So, we can say, students, that repulsion is the surest test of magnetism. Attraction can be caused either by the opposite poles of the magnets or between one pole of a magnet and an unmagnetized bar of iron. That means an iron piece can get attracted. A magnet can also get attracted, but only a magnet can get repelled with a magnet. So, repulsion, student, is the surest test to find whether a substance is a magnet or not. Okay. Now, in this activity, we are going to learn a new thing, that is magnetization. Now, what is magnetization, students? Magnetization is turning a magnetic material into a magnet. Now you may ask, can we even do that? Now if you remember the definition of magnetic materials, they are defined as those materials which can be attracted to magnets, plus they can be converted into artificial magnets. Now we are going to learn the process of doing so. In doing so, we may require some of the materials. Those materials are penned down here, students. The first material is a steel strip. That means you have to take a lengthwise long strip of steel that is easily cut by a knife or a scissor. Okay. The second component that you require to magnetize is a bar magnet. So what you are going to magnetize, students? You are going to magnetize the steel strip. And what we are going to use to magnetize the steel strip? We are going to use the bar magnet. Apart from this, we also require a magnetic needle. Now, why do we need a magnetic needle? We need a magnetic needle to test whether our steel strip has converted to a magnet or not. So, let's begin with the activity, students. For beginning the activity, first consider the first diagram. Okay. The first diagram, you can see there is a steel strip kept here, and we had termed its edges to be A and B. Right, students? So, we had kept the steel strip on a wooden table, say, and we had kept it on the edge so that it does not go anywhere, and we termed the edges to be A and B. Now, we'll take our bar magnet, and what we're going to do? We are going to start rubbing the bar magnet over the steel strip. Now, to understand this, let's understand this. Let's say my hand is the steel strip and this is my bar magnet. So, what we are going to do? We are going to move the bar magnet in this direction. Once it reaches the other edge, we will lift it up and we'll again put it on the last edge. We had started making the movement, then we again make the movement. We again pick it up, we again keep it, and we repeat this activity for at least 40 times. Now, once this is done, we need to test whether our steel strip has been magnetized or not. For this purpose, we will use our magnetic needle. Let's say you suspend the magnetic needle, that means it is free to move. Now, when we bring our steel strip near the steel strip we have magnetized, the same steel strip that we have magnetized, if we bring it near the needle, the freely suspended needle, you may observe that while bringing the A part on which we were rubbing the bar magnet from north direction, from the north pole, when we are doing this and bring the bar magnet near the magnetic needle, you will observe the needle will deflect and it will go in the opposite direction from the steel strip. Why? Because on doing so, our steel strip has been magnetized, and when it has been magnetized, it will have its poles, right? Now, where does these poles have been developed? Now, students, you know we use the north pole and we rubbed starting from the side A. So, on doing so, our A side of the steel strip became the north pole of my magnetized material, and the B side becomes the south pole. So, if I bring not the A side but the B side towards the north pole of the magnetic needle in this case will be attracted towards the steel strip. This shows that you can magnetize any magnetic material by employing the same method. If I have used the other pole, then my whole setup would have turned vice versa. That means if I use the south pole of the bar magnet to magnetize my steel strip, then my A part would become the south pole. On the other hand, my B portion will become my north pole. Okay, students? Till now, we had already understood about attractive property, directive property, and we have learned about the poles of the magnet. We also learned, students, how to magnetize a magnetic substance so that we can convert it into a magnet. Okay. So, in this activity, we are going to extend the same learning. Now, let's say I use this thin strip and magnetized using my bar magnet given here. My thin strip AB on magnetizing get converted into a magnet by developing the north and the south pole on the two edges of A and B, right? Now, if you remember, students, in this activity, we use the steel strip that could be easily cut, right? So, now we are going to use the same magnetized strip and test one more property of the magnets about the poles. Now, what is that property? We will conclude it at the end. Now, for the first beginning, let's say you magnetize the steel strip and it is placed here. So, this is nothing but our magnetized steel strip, right? AB. Now, on magnetizing, we understood that the north pole is on the side where we started to magnetize, and the other side becomes the south pole. Now, using a scissor, just cut the strip into half. Let's say I cut the strip from this point. On cutting the strip, what do you get? You get two strips of magnetized steel. Okay. Now, what we are going to do, we are going to test these strips for magnetic material. For that, students, we used a magnetic needle. So, in this case, let's say we named it AC and DB. The two strips are named as AC and DB. Now, we have to test what are the polarity, what are the poles that developed on these strips. So, for this, what we have to do, we have to bring each end one by one near the magnetic needle. So, let's say in case number 1, we brought the A portion of the steel strip near the magnetic needle. In this case, as this is my north side and my magnetic needle's north is there, it will be repelled. That means it is confirmed this is my north side, right? On the other hand, what I can do? I can bring the C towards the north pole of the freely suspended needle. So, if instead of A, I bring C, now we know if the magnetic needle gets repelled, it is the north pole. But if it gets attracted, it will be the south pole. So, when you will bring the C portion of the steel strip near the magnetic needle, you will see it is getting attracted to C. That means my C developed into a south pole. On cutting my steel strip, it did not get cut into north and the south pole individually, but my each individual strip of the steel, that is AC and DB, gets its own north and south pole. If you want to retest, now we will use the other strip, that is my strip DB. In this case, we already know B side of the steel strip was what, students? It was south. So, when we bring the B side towards the north of the needle, what will you observe? You will observe attraction, right? That means this needle is attracted to the B side of the steel strip. But what about D? D was not any pole earlier, but when we cut it, it developed a pole. Now, to test which pole is developed, we have to bring the D part of the steel strip near the magnetic needle. On doing so, students, you will again observe while I bring the D side, the magnetic needle is repelled. That means my D part of the cut steel strip has developed the north pole. Students, this is a very important point, that even if after cutting a magnet into thousands of pieces, each piece will develop its north and south pole. That means each piece will have its own north pole and its own south pole, irrespective of how small or how big it is. This is a very important property of magnets. It always have two poles. Okay? It always have two poles. So, even if I cut it in 2 pieces, 4 pieces, or let's say 8, 16, any number of pieces, all pieces will have the two poles. Okay, students? So, we can say it in a statement such as, when a magnet is broken, then each broken piece is a complete magnet with both the poles in it. Thus, magnetic poles always exist in pairs. You cannot have an individual north or an individual south pole. Your magnetic poles will always exist in pairs. Okay, students?
Now, in this investigation, we are going to learn about the magnetic force and how strong it is if we compare it to other forces. Now, you know, students, that a magnet can attract magnetic substances. But can a magnet also attract magnetic substances from a distance with another material inside? The answer would be yes. And we are going to prove it by doing an investigation. In this investigation, you need to take some iron pins. Let's say 50 pins. Okay. And you are going to place it over a wooden table. Now, we know that iron pins are magnetic in nature. They are magnetic materials, right? But wood is non-magnetic. That means you cannot attract wood using a magnet, right? The next thing I will need to do the investigation is a bar magnet. Now, what you need to do, students, when you place 50 pins over the table, you need to bring the bar magnet from the below of the table and you need to stick it where the pins is. Now, how we will check whether the pins actually got attracted to the magnet? You need to move the magnet to left and right. Now, when you will do, students, when you move your magnet from one side to another side, you will see the pins over the table also move along with the magnet. That means the magnet is so strong that it can attract the magnetic material even though there is a barrier of non-magnetic material. That means if I have to say it in one line, the magnetic force can attract the magnetic material even through a non-magnetic material. Okay, students?
Laws of magnetism. Now, before this, we should know what we are learning in this. In this unit, we are learning about various properties of magnet under the unit of properties and uses of magnet, which falls under the theme of magnetism. Till now, you already learned what are magnets, how then you magnetize material, how can you test various properties of magnets, and what are magnetic and non-magnetic substances. Now, in this last activity, we are going to establish one more concept of whether an artificial magnet or a substance that has been magnetized can lose its magnetism. The answer would be yes, it can. So, before that, we are going to use the basic knowledge that we had already gained. Do you know how we can magnetize a magnetic substance? Now, a magnetic substance are those substances which have the tendency to get converted into a magnet, and thus they are also attracted to magnets. Now, to magnetize a magnetic material, you need a magnetic material. Let's say we take a nail, and you need a bar magnet or any magnet which you can use to magnetize your magnetic material. In this case, we are using a bar magnet and a nail. Now, to magnetize the nail, what we need to do, let's say this is my nail and this is my bar magnet with my north and south pole. Now, to magnetize the nail, I have to pass the magnet over and over the nail multiple times in the same direction. So, let's say I am making the magnet pass over the nail in this direction. So, I will be repeating that activity over and over again. Let's say I repeated the activity for 40 times. Then, I need to check whether my nail got magnetized or not. For that, you can use a freely suspended magnetic needle. Now, a magnetic needle is a very thin piece of magnet that is allowed to move freely. Now what we'll do, we'll bring the nail near the two poles of the magnet. Now when we are making a magnet, you have to take into consideration all the properties of the magnet. You know, whenever a magnet is created, it is not an individual magnet. It will always have both the poles, that is the north and the south pole. Let's say the head of the nail becomes the north pole and the tail becomes the south pole. So when I bring the north pole near the south pole, what will you observe? As we know that the poles of a magnet attract, this will get attracted to the nail. But on the other hand, if I bring the tail towards the south pole, we will see that the needle gets repelled, right? So this is how we get to know that the nail gets magnetized. But student, what will happen if I hammer this nail? I have my nail like this. Yes, students? And I use a hammer, a light hammer, and I hammer it. Let's say 4 or 5 times I am hammering my nail. What will happen? Will anything change? To do that, we again have to test our magnetized substance using our magnetic needle. So, we'll again bring the nail near our magnetic needle, and in this case, you will see that it will be attracted by both these sides of the needle. That means, in this case, it is just acting like a magnetic substance and not like a magnet. That means what we had seen, because of hammering of the nail, when we hammer the nail lost its magnetization. That means we can pen it down in one way. A magnet loses its magnetism if it is heated, hammered or mishandled. That's why you always have to store your magnets very properly. Okay students, thank you.